Alright, in this video I wanted to talk about Boolean theorems. We use Boolean theorems to help us with Boolean algebra. Boolean algebra is a mathematical technique that provides the ability to algebraically simplify logic expressions. These simplified expressions will result in a logic circuit that is equivalent to the original circuit, yet requires fewer gates. Okay, so what we're going to talk about in this video is single variable ones. So we're going to go over some theorems for AND functions, OR functions, and inverter functions. So let's start with the AND functions. So we've got 4 single variable theorems that apply to our AND functions. Theorem number 1 is if we have x and a 0, that our output is always going to be 0. So you can see that with our AND gate here. You got x and 0 is always going to equal to 0, and we can prove that with our truth table here. So no matter what x is, if the other variable is 0, it's always going to be 0. Okay. Our second theorem, theorem number 2 for our AND functions here, x and 1 is equal to x, right? So we can see that here. No matter what x is, if the other one is 1, it's going to be up to what x is. So if x is 0 and 1 is going to be 0, but 1 and 1 will be 1. Okay. Theorem number 3 states that x and x is going to be equal to x. Okay, so if we're looking at our truth table here, your both inputs are x, so they have to be the same. So if my inputs here are the same at 0, my output's going to be 0, and my inputs down here are the same at 1, which makes my output 1. So if x is 1, output will be 1. If x is 0, output will be 0. Theorem number 4 states that x and not x are going to be equal to 0, right? So this is an AND function. If x is 0, that means not x is 1, and the output is going to be 0. If x is 1, and that means not x will be 0, and my output will be 0. So that's our 4 single variable AND function theorems. We've also got 4 single variable OR function theorems. This first one, theorem number 5, x or 0 is going to be equal to x. So we got x or 0 is going to be equal to x. We can look at our truth table here. X or 0 is going to be equal to 0, but that's if x is 0. If x is 1 down here, so 1 or 0 is going to be equal to 1. X or 1 is always going to be equal to 1, because no matter what x is, you'll have a 1 on the other side, which gives you an output of 1. X or x is going to be equal to x. If you've got the 2 equal here, they're both 0, your output's going to be 0. They're both 1, your output's going to be 1. Theorem number 8 states that x or not x is going to be equal to 1, right? So if x is 0, that means not x is going to be 1, and since this is an OR function, it's equal to 1. If x is 1, it means not x is 0, but that doesn't matter because it's an OR function. If x is 1, the output is 1. Okay? We've got one more single variable theorem for our inverter function, and this is theorem number 9. Okay, and this states that not x is going to be equal to x. Okay, so if we take x and we run it through an inverter, you get not x, and if you run it through another inverter, which flips it back, you get not x. And if we look at a truth table here, you run it through the inverter once, it flips. You run it through the inverter again, it flips back, and you get not x is equal to x. Alright, so I want to run through Just a couple examples here about how to use this. If you have a logic expression, you want to simplify it so that way you can use less gates to create your circuit. So this first one, we have F1 is equal to A and B, or C and not C and D. Okay, so if we're looking for our solution here, if we take theorem 3, we can say that A and A is equal to just A, and we can look at our theorem 3 here, x and x is equal to x. So if we have A and A, that's equal to A, which would leave us with A, B, or C and not C and D. Then we can use theorem number 4 here, which if we're looking at theorem number 4, we have x and not x are equal to 0. So C and not C are going to be equal to 0 over here, which gives us A and B, or 0 and D. If we use theorem number 1, which is x and 0 is equal to 0, we've got D and 0, so we've got D and 0 is going to be equal to 0 here, which gives us A, B, or 0. Theorem number 5 states, looking at theorem number 5 here, x or 0 is equal to x. So we can use that here, which means A, B, or 0 is going to be equal to AB, which leaves us with just AB. We can't simplify that anymore, which gives us F1 is equal to AB. So we're able to use some of our theorems here. We took F1 is equal to A and B, or C and not C and D, and we simplified that down to F1 equals A and B. Okay, so we're able to get rid of C completely and D completely, and we just get A and B. Alright, I've got one more example for you guys for this section here. It's a bit of a longer one here. So we've got F2 is equal to B and not C, or B and not C plus, or not A and B and 1, or A and not B and 0. Okay? So the first thing that we're going to do is we're going to use theorem number 3 here, which is x and x is equal to x. We're going to use that guy twice. So we're going to use theorem number 3 twice. What we're going to do is B and B is equal to B, and not C and not C is equal to not C, which would leave us with B not C plus B not C, or not A B1, or A not B 0. Next theorem that I want to use is theorem number 7. So if you're looking at theorem number 7 here, is x or x is equal to x. Okay, so that means if we grab that, we can know that B and not C plus B and not C is equal to B and not C. So that means we can combine those guys. We get B not C, or A not A, sorry, B1 plus A not B 0. Next theorem I want to use is theorem number 2, which is our x and 1 is equal to x, which means we can get rid of that guy. So B and 1 is equal to not A, B. So we get B not C, or not A, B, or A not B 0. Theorem number 1 tells us that if we AND anything with a 0, it is equal to 0. So that means A not B 0 is equal to 0. So we get B not C plus not A, B plus 0. And theorem number 5 tells us that if we have anything ORed with a 0, it is just equal to that first variable, which gives us B not C plus or not A, B. So F2 is equal to B not C plus not A, B. And that is our final answer for that guy. Alright, so that was just a quick video with a few examples about our single variable Boolean theorems. There are a few other Boolean theorems that we will cover in future videos.